Let's do an overview of the component method for vector addition in 2 dimensions. The problem is you cannot add vectors in polar form. You must convert from polar to x and y components. Those can be added algebraically. X components separately, y components separately. Then the resultant vector R is a single vector that replaces all the vectors being added. We must report the vector in polar form or magnitude and direction. So, 3 steps: polar to component conversion, then add the x component separately, add the y component separately. The A vector, for instance, here, its magnitude is the length of the vector. When you draw vectors, the magnitude is proportional to the length, and so what will happen is we will form a reference right triangle where that magnitude will become the hypotenuse, from the tip of the vector to the x and not the y axis, regardless of quadrant. Then the x component will be the adjacent side. The cosine is the adjacent side of the hypotenuse. The y component will always be an opposite side, and the sine function is the opposite side over the hypotenuse. The largest side of any right triangle is the hypotenuse, is the angle opposite the right angle. That is the polar magnitude. So, sine is the adjacent over the hypotenuse, and so the cosine for the A vector, that's 20 degrees, is the adjacent, which is a sub x, meters cosine of 20 degrees, and this is where the 11.3 comes from. So that is equal to 11.6. It's a sine, and so that is hypotenuse, or 12 meters, times the sine of 20 degrees. The same process is used to decompose vector B into its x and y components, and those are recorded here. The x components are added algebraically, and so the sum of 11.3 and 12.5 is the 23.8 that we see here. And the sum of the y components, the 4.1 plus the 21.7, that is the 25.8 that we see here, calling the fundamental property that when we put vectors tail to tip, and so we draw the resultant x component from the origin to its end, and then from there we place the tail of r sub y to the tip of r sub x, and then the resultant vector, in this case, this is just simply the resultant of adding the x and y component, which is the vector itself, gives us the resultant vector. The resultant vector in polar form, which is magnitude, that means I write the R, I don't write the arrow over the top, angle theta. So if we look at the picture here, what we see is that the magnitude of the resultant vector is simply the hypotenuse of a right triangle. This tells us that the resultant is simply the Pythagorean theorem, or the square root of the sum of the squares. The direction. The direction is an angle from 0 to 360 degrees. This is the first quadrant, so we'll just call it angle theta, instead of theta ref for the other 4 quadrants. So we note that the angle theta has an opposite side that is r sub y. It has an adjacent side that is r sub x. We understand that the tangent function is the opposite side over the adjacent. However, we do not want the tangent. We do not want the ratio of r sub y to r sub x. We want the angle whose tangent is r sub y over r sub x. And so that's an inverse trig function. Tangent minus 1 on your calculator, where minus 1 means inverse function. That is not an exponent. And so on your calculator in the degree mode, you press tangent minus 1, left paren, r sub y, in this case 25.8, divided by r sub x, 23.8, closed paren, which will turn out to be 47.3 degrees. And that's it for right now.